Swayam Prabha. Digital India. Educated India.
So we are live, you can start your session.
Thank you. I welcome all the students, participants to this course on aerodynamics, which has been running for the last several weeks. And we are really thankful for your very wholehearted participation in the discussion forums. And we have also got some queries that you posted in the Google form. So now over the next hour or so, we are going to basically address those queries and questions and have a discussion so that you can benefit out of this interaction. I'll share a document now. So this is the first time we are meeting live for this course, Fundamentals of Theoretical and Experimental Aerodynamics, live session 1, 28 February 2022. And let me introduce you to my team. So myself, Professor Arnav Roy from Department of Aerospace Engineering, IIT Kharagpur, very ably supported by the course TA students, Mr. Arpit Mishra and Mr. Arjun Garva, who are research scholars of Cryogenic Engineering Center, IIT Kharagpur. So they are interacting with you regularly. I'm aware of that. So let's move on to some of the very interesting questions, queries that you have posted. And I thought that because many students have posted this query regarding calculation of normal and axial force acting on an airfoil, I thought that we need to have a detailed discussion on this once again. So I have put clippings from my lecture notes. As you can see over here, we have shown the airfoil section with the leading and trailing edges, the thickness distribution, the running coordinates, SU, SL, etc. And we have mentioned the sign convention for theta whenever we are looking at the a specific point on the airfoil surface, either it's on the upper surface or on the lower surface, and again closer to the leading edge or closer to the trailing edge respectively. So the sign convention that we have been following is that theta is considered positive when measured clockwise from the vertical line to the direction of P and horizontal line to the direction of tau. So that's the pressure and the shear stress that we are talking about. So at a point like A dash, for example, which is closer to the leading edge and on the upper surface of the airfoil, a theta would be considered to be negative over here, and therefore the sine theta works out as negative, cos theta as positive, while at a point closer to the trailing edge, which we are marking as A, for example, here theta is positive, and therefore both sine theta as well as cos theta are positive. And then we have written an expression for the elemental, normal, and axial forces as functions of pressure, the shear stress, as well as the inclination. Now, we are doing a little bit of a detailing over here just to make sure that we get the points clearly. So we are referring to this figure as 1, this as 2, referring to the points A dash and A respectively. We had prepared a table where we looked at the signs of these different terms, NUP, NU tau, AUP, AU tau, etc. And we are trying to argue here in more detail that how we can show that these signs are consistent, both from the equation perspective as well as from a more physical argument perspective. So when we look at the physical argument part, for example, when you look at a point like A dash, and you look at how pressure is acting on the surface, as you know, pressure always acts into the surface and normal to it, and shear stress always acts tangentially, and in a sense that it tries to tug the body back when the flow takes place. Therefore, essentially, it is acting in a sense of the flow direction. So we are assuming, of course, that the flow is approaching the body from the left. So in that situation, we can expect that the NUP would be negative because it's pointing along the negative y direction. And that's because P is pointing downwards. And then since tau is pointing upwards, Nu tau is expected to be positive. According to the sign convention, theta at A dash is a negative value. And therefore, the pressure contribution minus Pu dSu cos theta will be a negative value because cos theta is greater than 0. And minus tau u dSu sin theta will have a positive value as sin theta is less than 0. Thus, the equation 1, which gives consistent signs for NUP and NU tau at A dash, is proved because from the physical perspective, whatever sense we are getting is exactly or consistently represented by that equation 1. Now, following a similar logic, AUP would be positive, pointing along positive x direction because P is tilted towards the right end, because here the inclination is such that it has the force that will arise out of the pressure will have a component towards the positive x direction, and AU tau would also be positive because tau is tilted towards the right. So from the physics point of view, these are the directions. And again, when you go to the equation, the consistent positive signs are maintained by these terms. Minus Pu dSu sin theta, it becomes positive because sin theta is less than 0. And again, tau u dSu cos theta remains positive because cos theta is again greater than 0. So we did a round of arguments where we could show that both from the physics perspective as well as from the equation perspective, we are getting consistent signs. Now, the point is that we would repeat this procedure for the other points. We move on to figure 2 to look at the point A. And then we can figure out, first of all, that the theta at A is a positive value, going by the sign convention. And then if you look at NUP, it would be negative because it points along the negative y direction. And because P essentially points downwards, tau is also pointing downwards. So Nu tau is also going to be negative. And then when you move on to the equations, you get the same sense because minus Pu dSu cos theta will have a negative value as cos theta is greater than 0. And minus tau u dSu sin theta will also have a negative value as sin theta is greater than 0. Now moving on to the second equation, that means for the axial component, NUP and NU tau at A would be following, rather, as far as the axial components are concerned, we look at the AUP and the AU tau. So AUP would be negative, pointing along negative x direction because P is tilted towards the left, and AU tau would be positive because tau is tilted towards the right. And the consistent signs come up from the terms of the equation as well, equation 2, because minus Pu dSu sin theta would be negative because sin theta is greater than 0, and tau u dSu cos theta would be positive because cos theta is greater than 0. So we got a kind of detailing here using these two figures and trying to argue both from the physics perspective as well as from the equations perspective that we do end up getting consistent signs. Now, we'll just continue with this exercise and we'll move on to the bottom surface of the airfoil. Let's do that exercise. And I'm thankful to the students because of their close scrutiny of the study material. Incidentally, I did come across a small mistake in the sign of one of the terms, which was creating some kind of an anomaly. So we'll discuss about that here. So here is the table, which shows the signs of the respective terms again. And we now have 2 points on the lower surface of the airfoil, B and B dash respectively. So we are showing the details in figure 3 and 4 respectively. And here are the two equations 3 and 4, which are important. And notice this correction over here in equation 4. So we continue with figure 3. So here we find that theta is a positive value. So from a physical perspective, of course, one thing that we need to notice is that because pressure is acting upwards, basically, it will have a positive contribution to the NLP term. And tau is pointing downwards, and therefore NL tau is expected to be negative. When you go to the equations, PL DSL cos theta will have a positive value because cos theta is greater than 0. Minus tau L DSL sin theta will have a negative value because sin theta is greater than 0. Therefore, the equation 3 gives consistent signs for NLP and NL tau for the point B. Again, we'll move on to find out the axial components. ALP would be positive, pointing along positive x direction because P is tilted towards the right, and AL tau would be positive because tau is tilted towards the right again. And the consistent signs are maintained by these terms, PL DSL sin theta because it's positive value coming from sin theta greater than 0. And this will actually be a positive term because cos theta is also greater than 0. So this is the correction. And when we move to figure 4, at the point B dash, let's complete with this exercise because this is the last point we need to look at. We expect the NLP would be positive because it's pointing in the positive y direction. Tau is pointing upwards, therefore NL tau is expected to be positive. According to the sign convention, theta at B dash is negative. Therefore, PL DSL cos theta will have a positive value, minus tau L DSL sin theta will have a positive value because sin theta is less than 0. And therefore, we come up with consistent sign. Going over to the axial part, ALP would be negative because it's pointing along negative x direction because P is tilted towards the left, and AL tau would be positive because tau is tilted towards the right. And consistent signs are maintained by these terms where PL DSL sin theta has a negative value, sin theta being less than 0, while tau L DSL cos theta will have a positive value because cos theta is greater than 0. So again, please note the corrections here. And I'm very happy that many students did go through this in detail and did find an anomaly. We'll get it corrected. I'll move on to a question posted by Mr. Lalit Sridharan V in the Google form that was circulated. So the question is regarding finite wings. The question is, in elliptic lift distribution, we know that the distribution of lift is elliptical and varies along the span. But from the derivation of lift, we are getting a value which doesn't actually exhibit that elliptic kind of a nature because it turns out to be a constant. So can we explain this? And the other question is that what is the difference between lift and lift per unit span? How does the formula of lift differ from lift per unit span? Of course, this question could be aimed at both finite as well as infinite wings, but I assume that this is again in connection with the earlier question. Let's go back to the basic figure that we drew when we discussed this topic, just to keep it in perspective. This is the lifting line theory model basically, and I hope you remember the important ingredients of the theory. So straight over to some of the important equations now. When we discuss about lift per unit span, we are essentially talking about a small unitary length scale along the y direction, and based on that we are defining this lift. In some books and literature, you might find this indicated with a dash, just to distinguish it from the total lift. Here, since we have literally mentioned that it's lift per unit span, we did not use this nomenclature. Please take this into account. So if you wish to use a dash in order to segregate it, it's always welcome. Now going over to the total lift L total expression, we basically get it integrated over the entire span. And for the elliptic lift distribution, as you may remember, that gamma y has an elliptic variation, and then we get it substituted into this above equation so that we get what we have here below. And then using a transformation, of course, we solve it and we get the result that you were talking about. Again, remember that that result that you have got in terms of the CL would work out like this, where the reference area comes into the picture. The S is the reference area which we are talking about. Okay, so here L dash was that lift per unit span, while this is the total lift that is acting on the planform of the wing. And we can show that when the lift distribution along the span of the wing is elliptic in nature, so is the chord length distribution. You may recall that even in my lecture, I had asked you to go back and refer some other books and references and find out how to do this problem. So I hope you have looked at it. So this is basically the difference between lift per unit span and total lift. And therefore, we have tried answering both your questions, that why it turns out to be a constant, even though the lift distribution is elliptic, because it basically comes out in that form after you integrate the expression. Let's move on to the next question. This was a question about vortex generation at the end of wing, basically wing tips. How this vortex is used by migration birds in delta formation for creating aerodynamic efficiency, and how birds use forward and backward stall in their flights. Okay, let's try to address the first question, which is of course a very classical and interesting question, that why these formations? And to begin with, first of all, what we need to look at is that whenever we look at these vortices being shed from the wingtips, they are essentially pockets of energy. And if there are trailing entities who can extract the energy from these pockets, they would definitely benefit. This is basically the concept of wake capture. That means you try to tap energy which is left in the wake of a flying object which is ahead of you. Now, when you talk about the formation flight, if you are looking at a leading bird and a trailing bird combination, then the trailing bird can situate itself in a leading bird's upwash if it laterally staggers itself, forming a part of the V structure. Let's try to explain with a very simple sketch. So let us say this is a leading bird's wing, and you have the vortex trailing from there, and you have a bird following very close in such a manner that it is able to capture the upwash which is created by the shed vortex. So that's what we are essentially talking about over here. So the trailing bird situates itself in such a manner that it can actually be located in the upwash region. And if that happens, then a lot of energy can be saved by the trailing bird, because it's being pushed upwards by the upwash left by the bird that is flying in front. And that happens only if you are maintaining a V structure. You can see that this actually will lead to a kind of staggering, and it can happen both ways, thereby leading to that V structure. And the V formation of bird therefore situates each flock member back and to the side directly in its neighbor's upwash. And in this manner, the upwash effect increases towards the trailing edge of the V formation. In this way, they can spend much less energy if they are closer to the rear part of the V. And then they can alternate their locations, giving the birds which are flying ahead a break. As far as flapping of these birds' wings are concerned, of course, they flap them back and forth, and they do change the orientation of the wing as well as they do so. So we basically talk about what is called as pronation and supination, so that they can do it in such a manner that they can efficiently lift themselves and again end up doing it with the least amount of effort. And for doing that, they have to alter their orientation very effectively. So you can read up a little bit more on these topics on your own as a part of home study. Thank you for raising such very interesting questions. And I can see quite a few participants. So I hope you are benefiting out of this interaction. Next question is from Ganesh. Is aerodynamics used in submarine design? Of course, yes. Many concepts of aerodynamics are kind of common to hydrodynamics, especially the incompressible aerodynamics fits in well over there, because in hydrodynamics, we talk about handling liquid flows, essentially water, over the submarine bodies. And that basically falls in the domain of incompressible aerodynamics. So many of the basic concepts, beginning from the concept of pressure, skin friction, lift, drag, aerodynamic moments, etc., all of them would essentially extend to bodies which fly, equally to bodies which fly in air, as they can be applied to bodies which remain submerged within water. There is, of course, one difference, that when submarines do come up close to the free surface of the water, then that is part of their journey, which is not very similar to what we see for aircrafts. So free surface would have wave structures, and the hydrodynamics could be significantly affected by the waves, which can create a different kind of force patterns, which are different from what it will be facing when it is deep inside the sea, much below the free surface. So there could be certain differences in that manner. And of course, there are also differences related to geometry, related to where the propelling device is located, related to the fact that they do not have very large wings. But in spite of all those, there are still a lot of similarities, a lot of scopes for application of this knowledge that you are acquiring in aerodynamics. Moving on to the next question, which is placed by Ranjit Kumar. So here's a question on thrust equation, which we covered in lecture 6. And he has a question about the term A. So if you recall, this was the sketch we had used, and we had referred to the cross-sectional area of the flow when we talked about this term A. And A was relevant to us at two locations, essentially. One was at the intake of the engine, the other was at the exhaust of the engine. And at the intake of the engine basically receives the ambient air at a velocity which is close to its own cruise velocity. And then it goes through a lot of processes within the engine. Its temperature and pressure gets raised significantly, and then it comes out of the exhaust side as a high velocity, high temperature jet. There are usually differences between these two areas, but for the sake of simplicity, here in this equation, we have assumed them to be equal. In general, you would find that the intake areas are larger than the exhaust areas. Next question from Simran. He's curious about principle of aircraft flow. So he wants to know whether Bernoulli's theorem or Newton's second law and change in momentum are relevant for aircraft flow. Of course, both are relevant. It depends on what you are looking at. For example, if you are looking at finding in what manner from point to point, as you study the flow past, say, a wing section of the aircraft, you'd like to see the change in static pressure, or you'd like to see the change in velocity, etc. As you know, as long as you are applying the Bernoulli's theorem to an appropriate situation, then you would have very reliable information about how these changes take place. You have to be careful about certain things, that when you apply it to a region where there are a lot of viscous losses, for example, within a boundary layer, you have to really apply it with a lot of care, because you have to account for losses in that equation. And then you have to be careful about rotationality or irrotationality. So you have to find out how to apply it across points in the flow in such a situation. So if you go through the section on Bernoulli's theorem once again, I think you can brush up on all these concepts. And again, to emphasize that, yes, Bernoulli's theorem certainly is of a lot of use if you want to do such calculations. But then, if you are interested in finding out forces and moments which are acting on the aircraft as it flies, then that's not the proper equation, because you have to look for Newton's second law in that case, so that you can find out the change in momentum that you are producing, which becomes responsible for the force and moment generation. So if you consider the aircraft as a kind of a black box, then you are receiving some kind of a flow pattern at the inflow side, and then you are observing another kind of a pattern at the outflow side. And if you perform some kind of a momentum conservation exercise within this black box, then certainly you should be able to get the forces and the moments that result out of it. So that's, of course, left as a homework problem for you. Think over it. And it's a very interesting question. And I think, I mean, you have to look at these equations from the application perspective. They are all relevant, but in different forms. Let's move on. There are quite a few more questions which we would like to address. There is one or two questions which I can see even in the live chat. I'll get back to those questions towards the end. So here is a question from Roshan Pradeep, a couple of them actually. This is related to lecture 1. And here he says that the examples in lecture 1 that we have given about the mathematical solutions for different flow types, he wants to know that how these are related to calculation of aerodynamic forces, and what type of solution will we get from such equations. Well, of course, when you are trying to solve equations to get forces and moments which act on a complete aircraft, then there is not much of an easy solution available for you. You have to solve for the compressible Navier-Stokes equations. But if you want to solve them, they are very, very expensive set of equations to solve on practical configurations like actual aircrafts. Okay, so they need a lot of computing power, and the simulations could run for weeks or maybe even months. It depends what kind of detailing, what kind of resolution you are looking at, and to what accuracy you are solving those equations. Accordingly, you have to employ your resources. But very often, when they design these aircrafts, there is an extensive conceptual design phase, and that is where you need ballpark estimates, you need quick solutions, and then you need simplified models. So whenever the need for simplified models come up, that is where you need to look at simpler equations. But then those equations should capture certain physics in essence, which is kind of in line with what those much complicated equations are trying to do. So you would have approximations, but in spite of those approximations, you would be able to get certain estimates, which are very, very important to be generated quickly at that conceptual design phase. And that's where the relevance of these models lie. So you would like to go for some amount of approximation, some amount of simplification of geometries, never mind, do them and get your solutions quickly. So that's the primary relevance. Next question is regarding lift and drag, which are, of course, two different, very different forces, and they are acting mutually perpendicular to each other. So how are they related to each other? Of course, we go back to the basics and state that yes, the source is again pressure and shear stress, but then they are ultimately producing a resultant force and a moment, and we are essentially trying to resolve them along orthogonal directions. That is where we see lift and drag coming up. Once we resolve, another way of resolving them, as you know, are a pair of normal and axial forces. So they have different relevances. But as far as aerodynamic efficiency is concerned, we are very, very much interested always to know what is that leverage that we are getting between lift and drag. Because if you have an ideal design, then what you are intending to do is spend nothing on fuel. That means you will have no drag, but all lift. Of course, that's an ideal machine. But that's basically the target. And that's why we are so very interested to look at those components. And in practical configurations, of course, we cannot imagine that, because as you know, as by now we have had extensive discussions on all this, that due to different effects like flow separation, skin friction, induced drag, and in the upcoming 6th module, you will also learn about compressible aerodynamics. There you will learn more about wave drag at high speeds. So those are the penalties that we end up paying. And then finally, the L by D ratio, which is the most relevant ratio in terms of aerodynamic efficiency, that does get compromised. But we have to keep our eyes open to this factor. And of course, to get to that factor, both of them, as long as we keep doing aerodynamics. Isn't lift associated with downforce and drag associated with thrust? Well, yes, but that association comes for a particular configuration in a very convenient sense. When you are looking at steady level flight, say of an aircraft, then you have a pair of forces which are balancing each other. So the lift is balanced by its weight, the drag is balanced by the thrust. So at that time, yes, you have this pairing of forces. But if you look at other parts of the flight envelope, then you have to find out more from your flight mechanics courses that how they relate. Thank you again for sending these very thought-provoking questions. A lot of students have sent questions of that kind. Next one comes from Yash Ashok Kumar Patel. He has a question on drag coefficient, and the question is related to why is drag coefficient of half sphere less than the full sphere, even though the boundary layer stays attached on the full sphere for a longer time? I'm not very sure whether you have something like this in mind, that you have a sphere which you have cut it into two. So you have a full sphere and you have a half sphere, and you are exposing both of them to a free stream flow like this. Well, my argument would be that this body is expected to have lower drag than this one, because the half cylinder would have a very large separation region over here. It's expected to be wider than this, and therefore the pressure drag probably of the half cylinder would be kind of more than compensating the higher skin friction drag that may be coming up in this case. You have to check this. All right, so I leave it to you also to think over it. It's a very thought-provoking question, but another thing that you need to look at when you answer this question is the 3D relieving effect. Okay, so if you are comparing between, say, a circular cylinder section and a sphere, you will find the drag coefficient of a sphere turns out to be smaller than the drag coefficient of a sphere of the same radius. And why does that happen? That happens because of what we call as the 3D relieving effect. So try to find out more on this. It's a little more exploration that you have to do to see whether you can answer the query that those two drag coefficients are not the same, though the cross-sectional geometry appears to be the same. Okay, the next question is coming up from, just let me spend a minute seeing whether we have more questions in the live chat. Okay, so we have a question from Topiwala Adit Dharmesh. He wants to know, how can the pressure remain constant for this lecture? So if I could get it correctly, we were discussing about flow past different surfaces. So one was the flat plate, the other was say an airfoil section pitched at a certain angle of attack. So the flow was essentially moving past a curved surface and facing adverse pressure gradient. We also looked at the airfoil lower surface where the flow was actually accelerating. So the dpdx in the two cases were different, because in the adverse pressure gradient case, this was becoming larger than zero. In this case, it was becoming lower than zero. In this case, it was equal to zero. And it is, of course, a very pertinent question. Let us try to answer it. When we are talking about the flat plate case, of course, we are talking about neutral pressure gradient, as we say. So dp dx equal to zero situation. And that, of course, is perfectly satisfied only in the inviscid case. And when you have a flat plate geometry, in an inviscid flow, this will be exactly satisfied. Because in an inviscid flow, the pressure gradient is purely a function of the surface geometry. On the contrary, when you have the viscous effects coming, there are two issues. One is the losses which are incurred in the stagnation pressure, and which essentially reflects in the static pressure as the flow moves along the surface, because the dynamic head remains conserved by virtue of the continuity equation. The other concept is that as the boundary layer forms, it also has a displacement thickness effect on the external inviscid flow. So those concepts we have tried to address over here in the paragraphs. Let's try to read through these lines. So though your question was referred to the flat plate geometry, I would like to mention the other cases also. So for example, the converging section will accelerate the flow. It will create a favorable pressure gradient. A diverging section will decelerate the flow. That's an adverse pressure gradient, and these are kind of intuitive to us. This is how the flow would also behave in the subsonic regime. However, in the upcoming sixth module, you will see that some counterintuitive things happen in supersonic conditions. That when you move a supersonic flow through a convergent section, it will get decelerated, while if you move it through a diverging section, it will get accelerated. So such things which are slightly counterintuitive will be seen in module 6. Now, getting back to what we were discussing, that when viscous external aerodynamics flows occur past various surface geometries, let us say an aircraft when it is in flight, the viscous losses are continuously incurred because of the formation of the viscous layers, the boundary layers on the aircraft surface. And that would obviously lead to pressure loss, but that's basically offset by providing the thrust force to the configuration. And the static pressure distribution is dependent on the external geometry. For very thin boundary layers, it's almost like an inviscid case. If you are studying flow through a channel or pipe, you need to pump it to maintain the flow due to pressure drop, as you have rightly pointed. And that's where the losses which are incurred in the boundary layers are actually showing up in the form of pressure drop, and you have to compensate that and therefore maintain that kind of pressure gradient so that the flow actually occurs. And as I said, that another aspect of pressure gradient that you have to be careful about is that this dp dx equal to 0 is, as I said, is perfectly satisfied only for inviscid flow. Now, for a viscous situation, you will always have a boundary layer, and therefore the displacement thickness effect So what it will end up doing is it will displace the external inviscid flow to a lesser or greater extent. Now this essentially means that in the external flow that would induce a slight pressure gradient anyway, because what is geometrically flat is fluid dynamically not perfectly flat as it appears to the inviscid flow. It looks a little more inflated, and that's basically because of the displacement thickness. So we now learned that there's also a pressure gradient which is sort of weak. It's a higher order effect, but it does exist, and it can be ignored for very thin boundary layers. Okay. The next question that we have over here, we have a question from Rajat Walia. He has two doubts, and that is related to lecture 29. This is a lecture related to the finite wing theory. So the question is that for infinite wing, why are we using the effective angle of attack in the lift slope integration? Based on my understanding, infinite wing should see a geometric angle of attack. There should not be any induced drag due to tip vortex formation. Well, it's a very nice question, and let me try to address it this way. That let's have the diagram here, which we had used in the lecture, which is trying to show the lift versus angle of attack for the two situations. One is the infinite wing, another is a finite wing. But when we mark the x-axis, we have to be a little careful. We are marking it this way that x-axis basically carries information about the alpha as far as the finite wing is concerned, while it is the alpha effective for infinite wing with the same airfoil section. But here, alpha effective has to be interpreted in connection with the finite wing, and that is where the catch lies. We have to understand that part. Remember that the zero lift angle of attack for both the cases are identical because we are essentially talking about the same airfoil section being used for both the finite as well as the infinite wing. Keeping that in mind, we are just citing a simple example here. So let us say that the geometric angle of attack for a certain test case is 12 degrees. And we are aware somehow that the induced angle of attack corresponding to that case is 2 degrees. And of course, once we know this induced angle of attack from by some means, if it is an elliptic wing, that means with a elliptic planform, then this induced angle of attack will also have no span-wise variation. We need to keep that in mind. So if we are trying to indicate this information in terms of slopes for what? Slope for the airfoil on one hand and slope for the finite wing on the other, then how are we going to translate that information? So if we pose the question in a slightly different way, that can we identify two angles of attack at which both the wings end up producing the same lift? That question can be answered by passing a dotted horizontal line like this, for example. So you identify two angles, one here, another over here, and you try to figure out that how are those angles going to be related. You will find that in order to correlate that information with the slope, then there is going to be a change in CL starting from 0 to where you reach, where this dotted line is, and you can say that that's delta CL. For achieving that, you will find that the infinite wing section would have to be pitched at 10 degrees angle of attack, while at the same time, the finite wing has been set at 12 degrees angle of attack. So what's happening? What is happening is that if we set the angle lower for the airfoil, even at that lower angle, we are able to manage the same lift, because though the finite wing is set at a higher angle, a few degrees are effectively going away from there through the induced effect. Therefore, when it comes to calculating slopes, interestingly, that induced effect comes back to the airfoil, because the airfoil is actually set at an angle which is lower by that induced angle, which produces the same lift. Now, if you put that information together, what it basically means is that the delta CL, which was achieved for an angle of alpha in the case of finite wing, is achieved for an angle alpha minus alpha I in the case of an infinite wing or an airfoil. And if you consider it to be thin, then you know that the slope, the DCL D angle of attack slope, is basically 2 pi in terms of radians. And then in this case, it is 10, and that 10 degree has to be converted into radians. That's what we have done here in the denominator. And the corresponding calculation in the case of the finite wing comes out like this: DCL D alpha is equal to delta CL by 12 pi by 180 degrees. And delta CL is what? Delta CL is basically this much. It is the gap between the dotted line and the 0 from where we had started, where the alpha, of course, was at the 0 lift angle of attack condition. Mind it that at that angle, both the configurations will function identically in an aerodynamic sense, because there's no induced effect at all due to the finiteness of the wing. And thereby, through this exercise, I hope you will be able to now better appreciate that the slope for a finite wing happens to be lower compared to the infinite wing. There's one more question from Rajat. Let's try to address that. So he says that while working on the slope of finite wing A and doing the integration, I'm not able to understand how are we equating A with A naught by, within brackets, 1 plus A naught by pi AR. Can you please explain this step in detail? Well, we have tried doing that, and how we do it is by integrating the equation that we just left behind for the airfoil case. If you integrate that, you will come up with an integration constant K. We leave it as it is, and we continue to assume that it's an elliptic wing, so that we have a nice expression for alpha I, and that remains constant all through your span. Having said that, now we are going to take a derivative of this equation. So if we take a derivative with respect to alpha, we'll have a DCL D alpha on the left hand side. And then what do we have on the right hand side? We essentially have A naught alpha, that's the first term. And then we have A naught CL divided by pi AR, that is the second term. Apart from the K, as you know that when we take the derivative, that will go to 0 anyway. So now if you take the d alpha of these terms, what are you left with? You are left with, you are going to get this. And then once you take this derivative, you will get A naught. And then within this expression, basically A naught by pi AR, this part is constant. So it just comes out as a coefficient. You are left with DCL D alpha. Now you have a DCL D alpha here as well as here. So get them onto one side. You have a new coefficient, 1 plus A naught by pi AR. And now if you send it to the other side, you have A naught by this expression. And since this is not equal to 0, therefore you will have a denominator which will be higher than 1. And that basically would mean that the DCL D alpha will be lower than A naught. That is basically the idea. So that tries to prove the point again that the slope of a finite wing will be lower than the corresponding airfoil counterpart. having said that, we are using the same lifting section in both the cases. So thank you very much for raising these questions. Some of them, some other questions we have already tried addressing in the discussion forum. Please keep posting questions of that kind in our discussion forum from time to time. Our TAs will be coordinating with you and also informing me so that I can address those questions as soon as possible. I'll just turn to the live chats for a quick look at some of the questions which have been posted there, trying to address a few from there. Many of you have wished me good evening, so I wish you all a very good evening, and I hope you are enjoying this session. You find it useful. Yes, certainly. Rajat says, can we get this PPT via mail? Of course, we can share this with you. Do not worry. Then there's a question from Sri Kishore, sir. Downwash happens at downstream of the finite wing, but how it is affecting geometric angle of attack, which is at the wing tip or ahead of the wing? Well, it is. It of course happens downstream, as you said correctly, and its effect continues far downstream. But incidentally, it is, its effect is kind of global in the sense that, you cannot confine it purely to a region which is far away from the wing. The wing will also get to see its experience its effect. It's because the source of the whole thing is happening at the wing tip, and therefore the effect will certainly come up there as well. I would suggest that you try to look up nice flow visualizations from the different sources that are available in the internet today, and try to figure out that through flow visualizations, can you picturize it better? All right. So if you do not manage to find one which can help you to explain or understand this point better, then you please let me know in the discussion forum. I'll try to post some visualizations which might also help you to get a better idea. Well, Adari Tej Kumar finds the course very tough. Well, Adari, I would say that, well, you would need to do a little bit more reading. You may be in your early years of college, so you may not have gone through a lot of detailing of some of the topics. So if you do a little bit of peripheral reading, I'm sure you will be able to answer the questions that we are raising in the different assignments, and you will be able to do better. Gabriel says, why are there thousands of airfoil made today which belong to supersonic, laminar flow? Okay, yeah, so very interesting question, Gabriel, that why do we need to have so many? Well, many a times what we find is that we have to tailor make airfoils for specific applications. So off-the-shelf airfoils may be a compromise for a given application, and therefore that itself is good reason to give introduction to a new airfoil. But again, there are other reasons. When airfoils are developed as a series, they may be systematically changing certain parameters starting from a base design to develop the characteristics in a very kind of easy to classify manner, and therefore that is another motivation for developing quite a few when they start a series. So there are different reasons behind it, but these are one or two reasons why that may be happening. The next question from him is, for airfoil boundary layer analysis computationally, is there much difference between inviscid and viscous boundary layer analysis? There are different ways of solving airfoil viscous flow problems. One is, of course, if you solve the complete Navier-Stokes equations, that is one possibility. The other possibility, other end, is solving it purely as an inviscid problem. And an intermediate possibility is that you try to do a boundary layer solution, find the displacement thickness and try to compensate the inviscid flow beyond the boundary layer by accounting for the displacement thickness. So this is an intermediate approach. Now, it would certainly matter, because if you do a boundary layer solution, at least you will have some idea about how your shear stress distribution looks like. Otherwise, you have no clue whatsoever. You could also predict perhaps that what could be a possible separation point if it is under an adverse pressure gradient. These things cannot at all be predicted with your inviscid model. Computationally, of course, the governing equations will be different. Yes. Does laminar separation bubble on airfoil only flows at low speed and low Reynolds number? Does this phenomena happen at high Reynolds numbers, not in supersonic speed, but speeds near to Mach 0.2, 0.25? Well, yeah, again, a very interesting question. So yes, laminar separation bubble is a typical low Reynolds number phenomena. If your Reynolds numbers really get high, you are very unlikely to see them. And that basically happens in a regime where you have a laminar boundary layer going quite some distance downstream of the leading edge, and then it faces an adverse pressure gradient. That's where the flow separation occurs initially, and then fortunately, if you have a transition in the shear layers, it will get reattached back, provided that the pressure gradients are not very adverse. These kind of happenings are rather rare at high Reynolds numbers and high Mach numbers too. Induced, well, this is a question from Rajat Walia. He says, induced angle of attack is constant for elliptic planform and total lift is elliptic for same elliptic planform, right? Well, we discussed about this, Rajat, in the earlier part of today's discussion, if you remember. So it would be nice if you can go back to that slide, which I'll be sharing, of course, as a part of the entire presentation. You could have a good look at it. And if you still do not understand that point, I think you can post a query in our discussion forum. We'll try to give you more details. Sri Kishore, thank you for joining. Thank you for participating. Rajat has a question. Is it possible to cover CFD aspects for aerodynamic problem in this course syllabus? Well, Rajat, just for the sake of completeness, I have spared 2 modules on CFD, which comes immediately after 6, I guess. The 7th and 8th modules will have some CFD content. Just to make the course complete, I have put in a little bit of CFD, but for a more comprehensive coverage on CFD, you can go through my course lectures on Introduction to CFD, which was run in 2020, later part of 2020. I hope you will find the lectures available in YouTube. Beyond that, if any one of you have more queries, whether it's related to theoretical or CFD or experimental aspects of some of the things we are trying to cover in this course, you are most welcome to post us those queries in the discussion forum. We'll try to revert as far as we can. So I hope I have addressed the queries which were posted in live chat, and for certain questions I could not spare a lot of time. I made it precise because of the time constraints. We do not have much time left perhaps for this session. So the first target was to address as many questions as possible in a brief way. So thank you, Yashwant. Thank you, all participants, those who could join today, and even those who could not join but are very actively following the course, trying to do the assignments, are planning to appear for the final exam and do the certification. You are most welcome, and we'll try to help you out with the course content as far as we can from time to time. So thank you once again. Be with us, and wish you all the best. Wish you happy learning, and I hope you find this course useful.
Thank you, sir. You can disconnect, sir.
Okay, thank you. So with that, I'm ending today's session. Again, thanking you all. We'll meet soon for the next live session, which will come up in a couple of weeks from now. Thank you.